determine the appropriate breaker size, wire size, and conduit size for connecting a 37.5 kVA 3-phase tri-transformer to an existing 400 amp 3-phase service, several factors must be considered. The transformer will be located approximately 60 feet from the service within the building. Firstly, let's address the breaker size. A 60 kA breaker is recommended. The secondary current rating of the transformer is not explicitly provided, but this breaker size is generally suitable for a 37.5 kVA transformer, assuming a secondary voltage of 110 volts. Secondly, we'll consider the wire size. For the secondary side, the 110 volt side, a 2 American wire gauge aluminum wire or a 1 American wire gauge copper wire is recommended. This selection is based on the transformer's kVA rating and the anticipated load of 12 receptacles. If the load increases beyond the initial 12 receptacles, the wire size may need to be adjusted accordingly. For the primary side, the 480 volt side, a 4 American wire gauge aluminum wire or a 2 American wire gauge copper wire is suitable. This choice takes into account the transformer's primary voltage, kVA rating, and the expected load on the secondary side. Thirdly, the conduit size needs to be determined. For the secondary side, using 110 volts, a 1 and 1/4 inch conduit is recommended. This size should adequately accommodate the number and size of conductors required for the secondary wiring. On the primary side, using 480 volts, a 1 inch conduit is generally sufficient to house the primary conductors. In addition to these basic sizing requirements, several other critical considerations should be addressed to ensure a safe and reliable installation. The circuit breaker must be rated for the available short circuit current at the service entrance. This rating ensures that the breaker can effectively interrupt fault currents without failing, which could lead to equipment damage or safety hazards. Surge protection devices should be installed on both the primary and secondary sides of the transformer. These devices protect against voltage surges caused by lightning strikes, switching operations, or other transient events. Without surge protection, sensitive electrical equipment connected to the transformer could be damaged by these surges. Proper grounding is essential for the safety and reliable operation of the transformer and all connected electrical equipment. The transformer enclosure, the neutral conductor, and all equipment grounding conductors must be connected to a common grounding electrode system. This grounding system provides a low impedance path for fault currents, helping to trip circuit breakers and minimize the risk of electric shock. The transformer should be installed in a well-ventilated location to prevent overheating. Dry-type transformers generate heat during operation, and inadequate ventilation can cause the transformer to overheat, reducing its efficiency and lifespan. Overheating can also pose a fire hazard. It's important to balance the load in the secondary side of the transformer to ensure proper operation. An unbalanced load can cause voltage imbalances, which can negatively affect the performance of connected equipment. Attempt to distribute the load evenly across the 3 phases of the secondary side to minimize voltage imbalances. It is important to note that the transformer secondary voltage was not explicitly specified. The assumptions used in this explanation are for a 110 volt secondary. If the secondary voltage is different, the wire and conduit sizes need to be recalculated based on the actual voltage. This recalculation will ensure that the conductors are appropriately sized for the actual current they will be carrying. Always consult the National Electrical Code (ONIC) and local electrical codes for specific requirements and regulations related to transformer installations. The NEC provides detailed guidelines on conductor sizing, overcurrent protection, grounding, and other aspects of electrical installations. Local codes may impose additional requirements or restrictions that must be followed. In summary, to properly hook up the 37.5 kVA transformer, you need to determine the breaker size, wire size, and conduit size for both the primary and secondary sides. For the breaker, a 60 kΩ breaker is likely suitable, assuming a 110 volt secondary. For the wire, on the secondary side, use 2 American wire gauge aluminum or 1 American wire gauge copper. On the primary side, use 4 American wire gauge aluminum or 2 American wire gauge copper. For the conduit, on the secondary side, use 1 and 1/4-inch conduit, and on the primary side, use 1-inch conduit. Always ensure that the breaker is rated for the available short circuit current. Install surge protection on both sides. Properly ground the transformer and all equipment, provide adequate ventilation, and balance the load on the secondary side. Finally, verify all calculations and selections with the NEC and local codes. To elaborate on the wire sizing calculations, it is crucial to understand the ampacity requirements for both the primary and secondary conductors. Ampacity refers to the current carrying capacity of a conductor, and it must be sufficient to handle the expected load plus any applicable dirting factors. For the secondary side, where a 110-volt system is assumed, the total current can be estimated using the formula kVA times 1000 divided by volts times the square root of 3. In this case, 37.5 kVA times 1000 divided by 110 volts times the square root of 3 yields approximately 196.8 amps. Since the system will initially power 12 receptacles, it's essential to consider the potential for increased load in the future. Each standard 15-amp receptacle is typically assigned a load of 180 volt amps. Therefore, 12 receptacles would have a total load of 2160 volt amps or 2.16 kVA. However, it's prudent to account for the possibility of additional loads being added later. The 2 American wire gauge aluminum or 1 American wire gauge copper wire sizes are selected to accommodate this potential increase in load. The ampacity of the conductors should be greater than or equal to 125% of the continuous load plus 100% of the non-continuous load as per NEC Article 210.19. For the primary side, where a 480-volt system is used, the calculation is similar but utilizes the primary voltage. Again, using the formula kVA times 1000 divided by volts times the square root of 3, we get 37.5 kVA times 1000 divided by 480 volts times the square root of 3, which equals approximately 45.1 amps. The 4 American wire gauge aluminum or 2 American wire gauge copper wire sizes are selected to handle this primary current, taking into account the anticipated secondary load. It is crucial to ensure that the conductors are properly insulated for the voltage level in each case. Conductors used on the 480-volt primary side must have an insulation rating of at least 600 volts, while conductors on the 110-volt secondary side can use insulation rated for 300 volts or 600 volts, depending on the specific application and local code requirements. When selecting the conduit size, consider the number of conductors, their size, and the fill requirements specified in the NEC Chapter 9. The NEC specifies the maximum percentage of conduit cross-sectional area that can be occupied by conductors. This fill requirement is intended to prevent overheating and ensure that conductors can be easily pulled into the conduit. For example, for 3 or more conductors, the NEC typically allows a maximum fill of 40%. Using the appropriate conduit fill tables, determine the minimum conduit size that can accommodate the selected conductors. For the 110-volt secondary side, where multiple conductors may be required to serve the 12 receptacles, a 1 and 1/4-inch conduit is usually sufficient. For the 480-volt primary side, where fewer conductors are typically needed, a 1-inch conduit is generally adequate. When selecting the breaker size, it's crucial to coordinate the breaker rating with the ampacity of the conductors and the transformer's primary current. The breaker's purpose is to protect the conductors in the transformer from overcurrent conditions such as overloads or short circuits. The breaker should be sized no larger than the ampacity of the conductors it protects, as specified in NEC Article 240.4. In this case, a 60 kA breaker is recommended based on the assumption that the secondary voltage is 110 volts. This breaker size is intended to protect the transformer and conductors from overcurrents while allowing normal operating current to flow. The available short circuit current at the service entrance is a critical factor in selecting the appropriate breaker. The breaker must have an interrupting rating equal to or greater than the available short circuit current at the point of installation. If the breaker's interrupting rating is less than the available short-circuit current, the breaker could fail to interrupt a fault, resulting in equipment damage, fire, or even explosion. To determine the available short-circuit current, consult with the local utility company or perform a short-circuit study. The short-circuit study involves analyzing the electrical system to determine the maximum fault current that could flow at various points in the system. This information is then used to select breakers with adequate interrupting ratings. Surge protection is essential for protecting the transformer and connected equipment from voltage transients. Voltage transients, also known as surges or spikes, can be caused by lightning strikes, utility switching operations, or the operation of inductive loads. These transients can damage sensitive electronic equipment, reduce the lifespan of electrical components, and disrupt operations. Surge protection devices, or SPDs, are designed to divert these voltage transients to ground, preventing them from reaching sensitive equipment. SPD are available for both the primary and secondary sides of the transformer and should be selected based on the voltage level and the expected surge current. Proper grounding is crucial for ensuring the safety and reliable operation of the transformer. Grounding provides a low impedance path for fault currents, helping to trip circuit breakers and minimize the risk of electric shock. The transformer enclosure, the neutral conductor, and all equipment grounding conductors must be connected to a common grounding electrode system. The grounding electrode system typically consists of a ground rod, a ground ring, or connection to the building's structural steel. The grounding conductor must be sized according to NEC Table 250.122, based on the size of the overcurrent protection device. Ventilation is essential for preventing overheating of the transformer. Dry-type transformers generate heat during operation, and inadequate ventilation can cause the transformer to overheat, reducing its efficiency and lifespan. The transformer should be installed in a location with adequate airflow to dissipate the heat. Avoid installing the transformer in confined spaces or near heat-sensitive materials. Ensure that ventilation openings in the transformer enclosure are not blocked. Load balancing on the secondary side of the transformer is important for maintaining voltage stability and preventing overheating. An unbalanced load can cause voltage imbalances, which can negatively affect the performance of connected equipment. It can also cause the transformer to overheat due to unequal current distribution across the phases. To balance the load, distribute the connected loads as evenly as possible across the three phases of the secondary side. Use a clamp-on ammeter to measure the current in each phase and make adjustments as needed to achieve a balanced load. Finally, it is crucial to consult the NEC and local electrical codes for specific requirements and regulations related to transformer installations. The NEC provides detailed guidelines on conductor sizing, overcurrent protection, grounding, and other aspects of electrical installations. Local codes may impose additional requirements or restrictions that must be followed. Obtain a copy of the latest edition of the NEC and familiarize yourself with the relevant articles. Consult with a qualified electrical inspector or engineer to ensure that your installation complies with all applicable codes and regulations. Furthermore, consider the long-term implications of the transformer installation. While the initial load may be limited to 12 receptacles, anticipate future growth and plan accordingly. Oversizing the transformer and conductors slightly can provide additional capacity for future expansion without requiring costly upgrades later. Also, consider the energy efficiency of the transformer. High-efficiency transformers can reduce energy losses and lower operating costs over the lifespan of the transformer. Investigate the available options and select a transformer that meets your energy efficiency goals. Regularly inspect and maintain the transformer to ensure its continued safe and reliable operation. Periodically check the transformer for signs of overheating, damage, or loose connections. Clean the transformer enclosure to remove dust and debris that can impede ventilation. Perform insulation resistance tests to assess the condition of the transformer windings. Address any issues promptly to prevent more serious problems from developing. Remember that working with electrical equipment can be dangerous. Always energize the circuit before working on any electrical components. Use appropriate personal protective equipment, such as gloves and safety glasses. If you are not qualified to perform electrical work, hire a licensed electrician. By following these guidelines, you can ensure safe and reliable installation of the 37.5 kVA transformer. Remember to consult with qualified professionals and adhere to all applicable codes and regulations. This will help to protect your equipment, your property, and your safety. Remember to always prioritize safety and consult with qualified professionals for any electrical work. The information provided here is intended for general guidance only and should not be considered a substitute for professional advice. Always follow all applicable codes and regulations and take necessary safety precautions when working with electrical equipment. In addition to the sizing and installation considerations, it's important to understand the basic operating principles of a three-phase transformer. A three-phase transformer consists of three sets of primary and secondary windings, each connected to one phase of the three-phase power system. The primary windings are connected to the incoming power source, and the secondary windings are connected to the load. The transformer operates based on the principle of electromagnetic induction. When alternating current flows through the primary windings, it creates a magnetic field that induces a voltage in the secondary windings. The ratio of the primary voltage to the secondary voltage is determined by the turns ratio of the transformer. For example, if a transformer has a primary voltage of 480 volts and a secondary voltage of 110 volts, the turns ratio is approximately 4.36 to 1. Three-phase transformers are commonly used in commercial and industrial applications to step down high voltage power to low voltages suitable for powering equipment and lighting. They offer several advantages over single-phase transformers, including higher efficiency through their power delivery and reduced harmonic distortion. When selecting a three-phase transformer, it's important to consider the kVA rating, voltage rating, impedance, and insulation class. The kVA rating indicates the apparent power that the transformer can deliver. The voltage rating specifies the primary and secondary voltages. The impedance is a measure of the transformer's resistance to current flow. The insulation class indicates the maximum operating temperature of the transformer windings. Another important consideration is the transformer's connection configuration. Three-phase transformers can be connected in various configurations, such as delta-delta, delta-Y, Y-delta, and Y-Y. The choice of connection configuration depends on the specific application and the desired voltage and current characteristics. Delta-connected windings provide high current capacity and are often used in power distribution systems. Y-connected windings provide a neutral point that can be used for grounding. In addition to the basic components of a three-phase transformer, there are several optional accessories that can enhance its performance and protection. These accessories include tap changers, which allow the voltage ratio of the transformer to be adjusted, cooling fans, which improve the transformer's heat dissipation capacity, protective relays, which detect fault conditions and trip the circuit breaker, and monitoring devices, which provide real-time information about the transformer's operating parameters. When installing a three-phase transformer, it's important to follow the manufacturer's instructions and all applicable codes and regulations. The transformer should be installed on a solid, level surface and securely fastened to prevent movement. Adequate clearance should be provided around the transformer for ventilation and maintenance. The primary and secondary conductors should be properly terminated and insulated. The transformer should be grounded in accordance with the NEC. Once the transformer is installed, it's important to perform regular maintenance to ensure its continued safe and reliable operation. The maintenance should include visual inspections, insulation resistance tests, and tap changer operations. Any problems that are detected should be addressed promptly. By understanding the operating principles, installation requirements, and maintenance procedures for three-phase transformers, you can ensure that they provide years of reliable service. Remember to always prioritize safety and consult with qualified professionals for any electrical work.